Alright, we're on day 2 of 10.4 looking at this particular homework assignment. So first of all, you had to do page 666, number 4 through 8, 9 through 12, and 702, number 10 through 12 all. I would like for you to get those particular problems up the board. Let me look at those. First of all, I think this would be, this is number 4 through 8. Yeah, I think you can get every single one of those up there. That'll be good for you. 9 through 12. Maybe just 9, so do 4 through 8 and 9 up on the board, and that'd be good enough. The rest of you, while they're putting those up at the board, you can write this down on the board, page 706, numbers 1 through 4, and we can be using those as practice. Of course, your proctor will have all the answers in front of you, or in front of them. They can read it to you. Alright, I trust that you got an opportunity to look over those particular problems. Of course, your proctor does have some answers in front of you. If you have specific ones that you want to ask me about when I return, feel free to, and we can talk through them. But of course, these would be slightly harder than what you're used to because they're at the end there, but they do cover all the major concepts. Alright, let's look at the new stuff for this particular lesson. So in this one, we're going to go all the way back to page 600 something. We're going back to 10.4. And so I will give you a page in just a moment. 664 is the page that we're going to be on, 664. Let's look at it. So they introduce a new concept. They talk about something called, actually, if you were with me before in the past, this actually isn't new at all. It says a polygon is an inscribed polygon if all of its vertices lie on a circle. So what I've done here is I've drawn you all of the polygons from three-sided triangle, quadrilateral, pentagon, hexagon, heptagon, octagon, nonagon, decagon, instead of a circle. In the past we said that something was inscribed if it was inside of a circle, and it's circumscribed if it's around a figure. So you'll notice inscribed polygons, here's 8 of them total. You should have each of those. Okay, 4 on top, 4 on bottom. And so a polygon is inscribed if its vertices lie on the circle. A circle is circumscribed if it goes around it. So circum means around, in means in. Alright, so this is the new concept. A polygon can be inside of a circle. From there, we have 10.9, theorem 10.9. And of course, this to me looks like it ought to be 2 different theorems. In fact, they even use the word conversely. So you should have 10.9 and then you should have 10.9 part 2, the converse to 10.9. But if it looks big, that's because it's really 2 rules in one. So it says this: if a right triangle is inscribed in a circle, then the hypotenuse is a diameter. Okay, so here's my circle. I've lost it on my copy paste, so here comes an ugly circle, I guess. So if you've got a circle, okay, and you've got your center, and it says if you draw a right triangle. So here's a point. Again, in order to make a right triangle, you got to have points, and so something like this, 3 points, by the way. If this is a right triangle and you're going to connect these pieces, then the diameter must go through the center. So we'll note the center for you, and so that's a right triangle. This is what they're saying. If a right triangle is inscribed in a circle, if it is to be inscribed, then its hypotenuse must be the diameter. It has to be. Notice, what would we call these other 2 sides? We call them both chords, and in a right triangle, the longest side is the hypotenuse, and in this case it's going to be the longest chord, and the longest chord in a circle is going to be the hypotenuse, and the diameter in this case is both. So the converse to that, and this is what they're saying, is that if one side of an inscribed triangle is the diameter of the circle, if one side of an inscribed triangle is the diameter of the circle, then, okay, here's my typo, sorry, you can just ignore this part, then well, I can just get rid of it. Then the triangle is a right triangle, and the angle opposite the diameter is a right angle. So what they're saying this time is, if one side of it is the diameter, if you have a triangle, and this piece right here is the diameter, then they said this is hypotenuse, side opposite it and that angle opposite it is 90 degrees. That's all they're saying. So if you have a right triangle at all, then the hypotenuse is a diameter. If one of the sides is a diameter, then it's a right triangle, and that's all they're saying. Give you a moment to write this down. Alright, here is example 4, and like I said in the past, this is exactly what it says. It's an example. There's no math involved. It's just something to show you. So it says, photography. Your camera has a 90-degree field of vision, and you want to photograph the front of a statue. You move to a spot where the statue is the only thing captured in your picture as shown. You want to change your position. Where else can you stand so that the statue is perfectly framed in this way? So you'll notice we've got our statue here, and you've got a right triangle. And so this particular person can stand here in his 90-degree field of view. He can see the whole statue, and it's all that's in his camera. So they even talk us through here. Here's the solution. And again, it's just an example. From 10.9, you know, and that's the theorem we just talked about, you know that if a right triangle is inscribed in a circle, then the hypotenuse of the triangle is the diameter of the circle. So what they did was, he can stand anywhere on a circle that's basically fixed about the point, anywhere on the semicircle that's outside. He can't stand in the statue. That's pointless. Then the hypotenuse of the triangle is the diameter of the circle, or you could say the statue itself is the hypotenuse, and therefore it's the diameter of the circle that you're standing on. And anywhere on that circle you will have a right triangle that you can actually see the whole statue. So the statue fits perfectly within your camera's 90-degree field of vision at any point on the semicircle. Cool. Acknowledged. Let's move on. All right, here's your new theorem. Theorem 10.10. It says, a quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. So, notice the words can be. That means that there are certain quadrilaterals that cannot be. And so, actually, let me point your eyes to the exercises that will be on page 667. 667, you'll notice numbers 20 through 25. They actually say, determine whether the quadrilateral can always be inscribed in a circle. So they got squares, kites, rectangles, rhombuses, parallelograms, isosceles, trapezoids. You can only put them in there according to 10.10 if their opposite angles are supplementary. That means they add up to 180 degrees. So just as an example, here's your circle, and again it's inscribed, but let's just pick one of the most easy ones. Here is a rectangle, and so we draw our lines, okay, the chords that make this up. It can be inscribed within the circle if and only if it's opposite sides. So here's X, here's Z, and so they say if they're supplementary. And so since this is 90, that's 90. 90 plus 90 is 180 across. Then yes, you can inscribe it in a circle. That's all they're saying. Also, that would be true going the other direction diagonally as well. So that's that theorem. All right, well, this sets us up for our new math in this particular unit, and you'll be surprised how easy this is. All right, let's look at example 5. All right, so you've got quadrilaterals that are inscribed in a circle, and it says find the value of each variable. Well, you can only, if they're inscribed in a circle and they're truly inscribed in the circle, you have to say, well, the opposite ones add up to what number? Okay, it didn't say that they were equal. That's not what it says. The quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. And so what we're going to say is then that you're going to link the 75 and the y, and they have to add up to 180. And so I can set up an equation with their opposite angles, so I can say y plus 75 equals what? You should be saying 180. And so then from there I'm going to take 75 from 180. This will leave me 105 degrees. And so that's the value of y. There you go. From there I can do the same with x. X plus 80 degrees equals 180. And so easy problem here. X is equal to 100 degrees. Okay. Now, yes, so this is 100 degrees and this is 105. All right. Now we've not said that those this is a parallelogram. We've not said any of those things, so we really don't know, but we could classify them further. All right, let's look at letter B. Letter B has kind of like a kite going on in there, but it says that the two opposite angles, so these two and these two, are opposites. Okay, well, opposite angles inside of an inscribed quadrilateral are supplementary, so they have to add up to 180. So we'll just start with the easy one here. 2a plus 2a equals 180. Okay, so that gives us 4a equals 180. Okay, and then a is equal to 4 goes into 18 4 times with 2 left over. 4 goes into 25 times, and so that should be a 45-degree mark. Now it says find the value of each variable. It doesn't say find the value of each angle. If it asked us to, that means that if this is 45, then both of those are 90-degree angles. Okay, that's all it's saying. All right, let's do the next one. So then we have 4b plus 2b equals what? Okay, and you'll notice in a lot of these examples, almost all year, we've just been adding up variables, setting them equal to 180, or we've been setting things equal to each other. And the processes haven't really been changing throughout the year. So you'll notice this particular one is 6b equals 180. Divide by 6, you're going to get b equals 30. And so that'll be simple for you. Now notice it doesn't say to find the values of the angles, but if we had to, this one would be 30 times 4, which would be 120, and this one right here would be 60. Now you should be able to look at these and say, okay, do those two look equal? Yes, they do. Do those two look like this one's double that one? Yes, it does. And so your logic should be true. Now, at the end of the day, and I didn't say this, these should add up to 360 because inside of a quadrilateral, the interior angles have to equal 360. And so you should be able to check that information on your own and make sure. Basically, what I'm saying is don't forget the stuff you've learned in the past. Okay? Use your logic and continue to move on. All right, let's take a moment and do these problems. You can do these at your seat / on the board. And so let's get these particular ones on the board, and then these two you can do at your seat real quick. But they should be pretty simple. Your proctor has the answers for all of these. But let's pause the video at this time and do those. All right, I trust you did well on that particular portion. And so now we've really only got one little thing left. And that is just your homework. And so as we come to the end of today's lesson, and again it's short, these last ones have been a little more active for you. These are the particular assignments that I have for you, and this is the last one, by the way, that is going to be videoed for geometry. And so I hope you enjoyed these. They took a little bit of time to do. Of course, they're not perfect. Nothing ever can be. I'm not using a tablet. That would help a lot with the coordination of writing. But I hope that it was helpful to you. Some of you are watching this at home. By the way, these can also all be viewed again at home. They're still online, and so you'd be free to go look these up and watch them again if you needed to, and you just feel like you didn't understand something. Whatever you need. So here is your homework. Write that down, and then of course you'll be dismissed at the bell. Thank you.